Hello, Randy Ruchti here. I'm presenting Radical, Radiation Hard Innovative EM Calorimetry, a group of individuals from University of Notre Dame, University of Virginia, Caltech, and the University of Iowa. Motivated by recent work on trying to understand how instrumentation could operate at conditions of high luminosity hadron-hadron colliders such as the FCCHH. Here, a sort of a schematic idea of an experiment that would be operated there in a document by Alexa et al. You can see that it has many different forms of instrumentation occupying central to end cap to forward regions. And the radiation fields are thought to be extremely severe in this environment. And our group is particularly interested in the development of electromagnetic calorimetry options that might be operative in these domains. The areas that you see right here that would be in the dark blue regions, and to be able to operate into eta values that might reach eta of 4. That's the objective. From Alexa et al., there's also an expectation of what the energy resolution should be like in such an environment, and that would allow the instrumentation to be effective. And the stochastic term for sigma E over E is roughly 10% over root E, and a constant term that would be of the order of 1% or less, with this holding up to eta values of 4 or so. In order to do this, you need to have fast response and superb performance. It says good performance there, but FCCHH is going to be very demanding. So the desirable features include, for us, very compact dimensions, excellent energy resolution, high efficiency, fast response, triggerability, good shower position measurements, so you can be able to identify these things over the very large number of background pileup. Radiation environment is going to be a challenging place in all of its forms, ionization and proton and neutron fluences, and transverse uniformity, longitudinal uniformity, and detective operation in the face of pileup. Those are all challenges. Our approach in Radical is to use an ultra-compact radiation-hard sampling calorimetry option using dense materials with a very small Moliere radius. Radiation lengths, 25 radiation lengths or more, but in an absorption length of material that's less than 1. And we're exploiting optical techniques because of the fast signal collection, and that involves scintillators, wave shifters, and very short optical paths. This is a diagram sketch of what such instrumentation looks like, built upon some earlier work that our group has been doing that began with Shashlik-style instrumentation for the CMS NCAP down select a few years ago. The instrumentation involves the sampling technique, which includes individual tiles of tungsten, 2.5 millimeters thick, interspersed with 1.5 millimeter thick lyso crystal scintillators. They form a sandwich of about 25 radiation lengths in depth. The Moliere radius for this structure is very small, 13.7 millimeters, and these modules, one indicated here, is 14 millimeters on a side, a square shape, and 114 millimeters deep. And the Shashlik-like structure, the light from the crystal scintillators, is read out by means of capillary structures that are radiation hard, that penetrate through the material and wave shift the scintillation light into wavelengths that are easily detectable with silicon photomultipliers or other such techniques. So the structures involve scintillator development, wave shifter development, optical transmission element development, photosensor development, and then the construction of these into modules, and then the testing of the same. So this is an interesting set of techniques. Many of them are very old in character, but the implementation is new. In terms of the scintillation materials, we're really emphasizing inorganic crystal scintillators or ceramic scintillators This is a table that my colleague Renwan Zhu from Caltech shows often, and in it, in the center, in this two columns, in the middle are lutetium orthosilicate, that's LYSO, or LUAG, lutetium aluminum garnet in the middle, and these are the materials that we're particularly interested in for their radiation hardness, as well as also their fluorescence efficiency. So scintillation materials of interest, LISO and LUAG, those two things I put in the column. They're doped with cerium or praseodymium, and in the case of cerium, it also has calcium co-doping. These materials, particularly the LISO, has been studied up to 300 megarads ionization dose, and neutrons close to 10 to the 16th, and protons also close to 10 to the 16th particles per square centimeter. They're going to survive to those doses, and the LISO and CIPM with photosensors, they are key elements of the CMS barrel timing layer. So a lot of this work has already been taken and is now being used effectively in current experiment for HLLHC upcoming. An additional feature is that the scintillating ceramics such as LUAG with cerium are even more rad hard than the LISO. And what does this mean? And here are two plots which shows the radiation-induced absorption coefficient in inverse meter units as a function of proton fluence on the left and neutron 1 MeV neutron fluence on the right. The black points are LISO, which is known to be rad hard. The purple, pinkish purple points are the LUAG, and those are a factor of 2 even better. So these are materials on which we have a clear eye on working toward the future, with the expectation that the LUAG, particularly LUAG in a ceramic form, might prove to be rather inexpensive compared to LISO, and a benefit when one wants to build an effective detector. Waveguides for collecting the the light from the tiles and wave shifting them. We have a new idea of fiber optic profiles in order to accomplish this. Instead of using plastic or organic fibers, which are radiation vulnerable, we use quartz capillaries with thick sidewalls to them. The core is either filled with a liquid wavelength shifter, as indicated in these filaments here on the left-hand side. You're looking at the ends of those. They can either be sealed on and polished on these ends with quartz itself, or it can be filled with a ruby quartz to block the light that would be propagating within the liquid core itself in the waveguide. And there are benefits to do one or the other of these. The benefits of no ruby core, that is the clear ends, you get a great deal of light. This has a suppressed vertical scale up to, and the units here are in ADC counts, 3000, whereas with the ruby quartz filler, that gives you a very, very uniform response, but the light level is lower by about a factor of 3 or so. So these individual plots that you see here, you start out with unirradiated capillary, and then every 50 megarads of cobalt-60 dose, you lose about 10% of the light from these systems, and there is adequate light to begin with, and after a long period of time, for example, at HLLHC operation or higher, these devices would still be operable. The thick wall is very interesting because the core wave shifter occupies a relatively small amount of fiber fraction compared to what would be a conventional wave shifting fiber. And the reason for this is that the light is propagating on the main through the quartz cladding rather than in the core, and that gives a much better optical transparency over radiation. These wavelength shifters and optical transmission elements have to be optimized, the shifters particularly for the scintillation crystals that we have. If the crystals are lyso-cerium or lyso-cerium-calcium, that emission is in the order of 420 to 425, and the wave shifters are called DSB1 or J2. Y11 also would work in this particular zone, but the DSB1 is particularly fast, much faster by at least a factor of 2 than those. For LUAG praseodymium, which is a very much a UV emitter, we have new wavelength shifting dyes based on hydroxyflavones that are capable of shifting that light up into the yellow-green. All wavelengths that are easily detectable with photosensors like SIPMs. The transmission elements can include capillaries filled with liquid, capillaries filled with inorganic or organic solid materials, just quartz fibers for Cherenkov detection, and there are also novel transmission structures that we're looking into as well. On the sensor development for detecting the light, we have two approaches. One is with silicon photomultipliers. These are Geiger-moded pixelated devices. They have been around now and used very effectively in experiments, and we're going from the larger cell structure down to very small structures. There have been a number of reasons for wanting to go these ways. One is for improved efficiency in the face of very high light levels, which are possible in EM calorimetry, and it provides longer wavelength detection, all important. These are already impactful. They're used in the CMS barrel timing layer. They're used in CMS HCal. And we're using them to detect the DSB1 emission and the emission from these other longer wave scintillators and wave shifters. This is a pulse you can see from a 5 micron scale-sized FBK pixel. Very fast, very rapid rise. We're also interested in the thermionic cooling for SIPMs. This idea originated within our program, the Radical program, but now it's being exploited on a large scale for the CMS barrel timing layer. And there are ways of using thermionic cooling both in the cooling mode and also in a heating mode, so kind of like a heat pump, to anneal devices when there is no beam, and this improves the overall performance of the instrumentation over time. We're also interested in the case of very high radiation environments to also have the kind of Geiger mode devices that will work similarly. SIPMs may not work to very high radiation dose levels, although we're going to push those as far as we can from our work, but that could include large band gap devices like gallium indium phosphide devices. These are fabricated. We have a number of these. Individual photon counting is seen, which is very much SIPM-like, as you can see here. Here's a photo of something where you can't actually see the pixels themselves. Here you see the photospectrum, and they're responsive. However, there are additional work that needs to be done here, even though the R&D has gone on for a couple of years now. There's a lot more work that needs to be done, and one of the challenges is, unlike for SIPMs, there's not really a broad commercial market yet. So this requires some careful work with vendors, which our group is exploring. We've done some testing with these kinds of structures in beams in the past, a few years ago, in preparation for the CMS NCAP calorimetry down select. We tested a matrix, a 4x4 matrix of these types of modules, very compact structure, read out with fibers or capillaries. The beam came in, and we were able to have electron beam energies at the CERN H4 line that went from of the order of 30 or so up to several hundred GeV. And you can see here for 100 GeV the nice spectrum of energy that was detected in these modules. So the resolution is very good. This gives a measurement of some of the performance obtained at that time, a stochastic term of 15.7% and a constant term that was below 1%. And more work has been done in the meantime, and we have a number of improvements where we are hoping that this will just get better as we work on it more carefully here and over a longer period of time. We have also, in these early days, a preliminary study of timing measurement. This was done a couple of years ago by Adi Bornheim in the Fermilab test beam in this particular case. And here a module was then studied, and the timing resolution for the signals that emerged from this device compared to very fast signals from microchannel plate devices showed that as the light levels go up, it's not a surprise, the light levels go up, the timing resolution can be improved, and it starts to approach values that are of order of 50 picoseconds. and that is in a very unoptimized and preliminary first look. So the question is, can we improve that further? And this is an area that has us greatly interested. So here's a new approach to timing that we're advancing and that we're going to be making beam tests of in the very near future here. And here's the standard module that you saw before. In this particular case right here, in one position in the module, instead of a capillary that measures the energy all along and throughout the module, we have instead a wave shifter positioned strategically at the location of shower max in that vicinity in the module. The rest of the capillary is filled with quartz rod. It's all fused. This is a solid device. There's no liquid wave shifter or anything in it. This is a prototype of the approach we're going to take, and you can read this capillary out from both ends. So the idea of reaching timing, measuring timing with such a module is you measure the time from shower max, where the number of particles is greatest, and you measure that at both ends of the capillary, and the estimation is that from simulation shows that at least in the Monte Carlo J-4 simulation value, how well we might do. These are electrons of 50 GeV that are directed into one of these radical type modules. This is the light yield and number of photoelectrons per MeV that you see, and as you improve the light collection, the actual timing resolution can reach below 20 picoseconds in this particular example. Okay, that's a simulation. Great to know that we might be able to achieve this. The trick is now, of course, to be able to show that in a test beam, but that's the idea of it. And we're making such capillaries, filaments, that would allow us to make such a measurement. So here in this picture that you see are two capillaries which are liquid filled. They're filled with liquid wave shifter. These are the capillaries that we've been currently using to measure the total energy of the shower coming out of the module, and the light is read from one end. The capillary in the middle is one of these new capillaries that has a wavelength shifting DSB1 filament right here at a location which would be shower max. The capillary is filled with solid quartz rod and fused to both ends, and the light can emerge from the downstream end and it can emerge from the upstream end, and we can measure the timing of the shower in the module by means of this particular light sensing element. So this will see the light from the LISO tiles located at near shower max in the module. That's the idea of it. In addition, we can expand on this idea and look even more deeply into shower development with these kinds of techniques. So here's a module shape. And in these modules, the capillaries that are filled inside can be filled with LUAG cerium fiber and then filled with quartz on either end. These various filaments can be placed at different depth locations, and the shower development as a function of depth can be used. This has a couple of benefits. One of them is measuring the shower development as a function of depth. The other benefit is you can also measure the development of showers that are passing through the structures at an angle relative to the axis of the structure. All important issues. So to summarize my presentation here, I've talked about Radical, which is this radiation-hard, ultra-compact EM calorimetry. We're interested in energy measurements. We're interested in shower max timing measurements. We're interested in understanding shower depth and shower angular measurements for profiling. And we're also going to be looking into the details of both scintillation and Cherenkov measurement, since our capillaries in part have significant quartz in the walls of the capillaries, or we can use quartz filaments. There are other areas of application in calorimetry, forward and hadronic. We can also think of these techniques in a broader use in scintillation wavelength shifting detection and also for timing detectors. Our work has been supported in part by the DOE, the National Science Foundation, and a nice grant to help during the COVID-19 period from the University of Notre Dame. Thank you for your attention. I'm stopping the presentation.